Now, so far, we've talked about solutions forming either spontaneously or not at all, but in reality, and in particular for solutions of solids or gases dissolved in liquids, there's a limit to how much of a solute can dissolve into any particular solvent. A solution that contains the maximum possible amount of dissolved solute at a given temperature is said to be saturated. If a solution contains a level of solute above the saturation point, a situation known as supersaturation, the solid solute will begin to undergo a process known as crystallization, wherein some of it will separate from the liquid phase of the solution and reform a solid. Sometimes, a supersaturated solution may not begin to crystallize right away and needs to be initiated. A good example of this is a solution of sodium acetate, which can exist in a supersaturated state for an extended period of time unless a so-called nucleation site is introduced to allow crystals to start growing, usually achieved by adding a small piece of solid sodium acetate. Once initiated, a large number of solid crystals start to form rather rapidly. Due to the appearance of this crystallization, this is sometimes called a hot ice demonstration. The name is a bit misleading since the solid formed is sodium acetate rather than water ice, but you can see the superficial similarity. As mentioned, solubility limits of compounds in water or other solvents are determined by temperature. In general, most solid solutes have higher solubility thresholds at higher temperatures, but the relationship is often nonlinear, and the temperature dependence of solubility varies a lot between compounds. For instance, glucose and sodium acetate are much more soluble in water at high temperatures than they are at lower ones, while the solubility of sodium chloride doesn't change very much at all with temperature. Furthermore, there are some exceptions, like cerium sulfate shown on this chart, that are solids with higher solubility at lower temperatures than at higher ones. Next, let's take a look at gas solubility in liquids, since it's distinct in many ways from the behavior of solids. First of all, gas solubility is determined by Henry's law, which states that the solubility of a gas in a liquid is directly proportional to the pressure. This diagram does a good job of illustrating how this works. Pressure is a measure of force per unit area, and if we increase the pressure, it makes sense that more gas molecules should be forced into the liquid than would be possible at a lower pressure. Besides pressure, the temperature also affects gas solubility. Specifically, almost all gases become less soluble in water as the temperature rises, as shown in this graph. This is the opposite trend seen with most solids. Notably, you can see that the solubility of oxygen decreases as the temperature increases. This is important for marine ecosystems because if water temperature becomes too high, the level of oxygen in the water can fall below levels required to sustain aquatic life forms. Gas solubility has many medical implications as well. In particular, hyperbaric oxygen chambers can be used to increase the pressure around a patient's body to increase the amount of oxygen that dissolves into tissues, which is important for treating conditions like gangrene. Another important implication is in diving. As you go further underwater, the pressure on your body increases. If you go diving with an air source, the amount of atmospheric gases, especially nitrogen, that can dissolve into your blood and body tissues when you breathe them is increased under the high pressures found underwater. This isn't a problem per se, but if you surface too quickly after such a dive, the solubility of the nitrogen in your blood will fall back to normal levels before it has a chance to readjust from the solubility levels deep underwater. This results in a very dangerous condition called decompression sickness, or colloquially, the bends, where gas bubbles of undissolved nitrogen form in various parts of the body. It can be avoided by surfacing slowly when diving, so that the gas solubility in blood decreases slowly enough to prevent bubble formation. Alright, let's get into colligative properties, which are the main application of some of these different ways of measuring concentration that we've discussed. Colligative properties of solutions are those that depend on the amount of solute dissolved in a solution, but not on the chemical identity of the solute. Phenomena associated with colligative properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. We'll start with vapor pressure lowering, which is described by Ralph's law. This law states that if we have a non-volatile solute, meaning that the solid has virtually no vapor pressure, as is the case with most solids, the vapor pressure of the solution will be lower than the vapor pressure of the pure solvent. Specifically, the vapor pressure of a solution with a non-volatile solute is the vapor pressure of the pure solvent multiplied by the mole fraction of the solvent in the solution. Let's see a typical example. The vapor pressure of pure water at 25 degrees Celsius is 23.76 millimeters of mercury. Given that information, What is the vapor pressure of a solution made by dissolving 1.00 moles of glucose in 15.0 moles of water at this temperature? Glucose, a type of sugar, is a non-volatile solute. After all, when was the last time you left some sugar out and saw it evaporate? To find the vapor pressure of this solution, we multiply the vapor pressure of the solvent, water, which is 23.76 millimeters of mercury, by the mole fraction of water. This is the number of moles of water in the solution divided by the total number of moles of all compounds in the solution. 1 mole of glucose plus the 15 moles of water. Effectively, we're multiplying the vapor pressure by 15 over 16. This gives a result of 22.3 millimeters of mercury. So you can see that the solution has a vapor pressure about 1.5 millimeters of mercury lower than that of pure water. Now that example was pretty straightforward because glucose is a covalent compound. Solutions of ionic compounds, on the other hand, often have lower vapor pressures than you might otherwise predict from Raoult's law. This is due to a couple of reasons. First, there are strong ion dipole forces between ions and polar molecules like water, so we have stronger intermolecular forces at play. Another factor is that when you dissolve 1 mole of, say, sodium chloride in water, it dissociates into 2 moles of separate ions, a mole of sodium ions plus another mole of chloride ions. The ratio, I, of the number of moles of particles in a solution to the number of moles of solute dissolved is known as the Van Hoff factor. Since a covalent compound like glucose doesn't dissociate in water, only dissolve, covalent compounds have a Van Hoff factor of 1. For ionic compounds, the value is higher. Usually it can be approximated by the number of separate ions in the chemical formula of the compound. So the predicted value for sodium chloride would be I equals 2. In reality, the experimentally determined value of the Van Hoff factor is usually a little bit less than the theoretical value. Not only that, but the Van Hoff factor for an ionic compound also depends on the concentration as well. As the concentration goes up, the Van Hoff factor typically decreases somewhat. There's no way to predict the experimental Van Hoff factor, so depending on the problems you encounter on the homework or tests, you will either have to use the theoretical value or an experimental value will either be provided or they'll at least give you a way to solve for it. The reason why the Van Hoff factor is less than the predicted value is shown here. When an ionic compound dissociates in water, most of the cations and anions will be hydrated, like we showed on a previous slide. However, there's always going to be a small number of ions that are only partially hydrated and paired together, acting as a single particle for the purposes of colligative properties. I've shown you the formula to calculate vapor pressure lowering and explained it in terms of intermolecular forces. But is there a mathematical description underlying the phenomenon as well? Unsurprisingly, the answer is yes. If we go back to our formula for calculating whether a reaction is spontaneous or not, let's consider the individual parts. A solution has essentially the same enthalpy of vaporization as the pure solvent itself, but as we saw earlier, a solution is a higher entropy state than the pure substances that make it up. As a result, the entropy difference between the vapor phase and the solution is smaller than the entropy difference between the vapor phase and the pure solvent. Therefore, the T times delta S of vaporization portion of the formula becomes smaller for any given temperature. This results in delta G being less negative or less spontaneous for the vaporization process. Hence, vaporization from a solution is less favorable than it is from a pure solvent.